Let's get started with Chapter 4, Section 2, as I recall. Yes. Elementary number theory and methods of proof, continued with direct proof and counterexamples, the writing advice. How do you go about writing a proof? Proofs for universal statements is up first. Over the years, these rules of style have become fairly standard for writing final versions of proofs. First, copy the statement of the theorem to be proved on your paper. This way, you know for certain what you're trying to prove, and you could refer back to it, and those that are going to be reading it can refer to it as well. So it's made perfectly clear what the theorem is going to be proven. Clearly mark the beginning of your proof with the word proof. This, like I said, separates the general discussion about the theorem from its actual proof. It's just a formatting thing. State the theorem, begin the proof, and mark those as being separate sections of the paper or whatever you're writing. Make the proof self-contained. This means you should declare any variables or symbols that you're going to be using that are not generally accepted. Declare them. It's kind of like in a computer program, you have, at least in C++, you have to declare your variables before you use them. Same type of thing. The symbols and variables that you're going to be using, declare them before you use them. State what they are or what they could be. Like say, suppose m and n are any even integers. You're stating what the variables are and what they contain. And any restrictions on that, like let x be a real number such that x is greater than 2. So declare the variables and what they are. At a later point in your proof, you may introduce a new variable to represent a quantity that is known at that point to exist. So you declare n as even. You can write n equals 2s for some integer s. You're declaring in this statement that you're going to be using s, and it is going to be an integer. So write your proof in complete grammatically correct sentences. Now, this doesn't mean you shouldn't be using symbols and that sort of, and equations and that sort of thing. Just when you're using those things, make it a statement like then m plus n equals 2r plus 2s. That's by substitution. So that's a complete sentence. Okay, and then you can continue it down. The then m plus n is implied equals to quantity r plus s by factoring out 2. So this subsequent equal sign would indicate that since this is true, this which also means this is true. So write and complete grammatically correct sentences so people can understand and it's clear what you're saying. Keep your reader informed about the status of each statement in your proof. They should never be in doubt as to whether or not something in your proof has been assumed or established or is still to be deduced. If something is assumed, preface it with a word like suppose or assume. If it is still to be shown, preface it with the words we must show that, or in other words, we must show that. This is important when you introduce a variable in rephrasing what you need to show. All right. Give a reason for each assertion in your proof. Each assertion should come directly from the hypothesis of the theorem or follow from the definition of one of the terms in the theorem or be a result obtained earlier in the proof or be a mathematical result that has previously been established or is agreed to be assumed. So you need to indicate the reason for each step in your proof. Like back here, it said by substitution. That's what the reason for that statement. It's by substitution. This one is by factoring out 2. You could also use by the hypothesis, or by definition, or by a theorem, that sort of thing. But each step needs to have a reason, a clear, understandable reason for the step. Don't assume that the reader knows the reason for a step. State it explicitly. Include the little words and phrases that make logic of your argument clear. Indicate how each sentence is related to the previous one. So you can start sentences with because or since and state the reason why it follows, or right then or thus or so or hence or therefore or consequently or it follows that, and include the reason at the end of the sentence. But those little words and phrases make it clear or clearer to the reader what steps are being taken and why. When you have the reason at the end of the sentence. Now, if you have a sentence that expresses a new thought that doesn't follow as an immediate consequence of the preceding statement, but is needed, introduce it by writing observe that, or note that, or recall that. Sometimes in a proof it is desirable to define a new variable in terms of previous variables. In such a case, introduce the new variable with the word let, like let s be an integer, and with a variable that's assumed to be even, and let s be an integer such that 2s equals n. And that would be by the definition of an even integer. Display equations and equalities. Do this on separate lines. It increases readability. You move down as you progress through the manipulation of the equation or inequality. It's easier for people to read, and it's also easier to check your work for accuracy. Now for variations among proofs. Everybody's different. Simple as that. How you prove one thing is going to be different from how the next person might prove the same thing. Even though the mathematical principles may be the same, how it's presented is going to be different. It's kind of like writing a history paper. Two people writing a paper on the history of the city of Jackson are going to write two very different papers. That's kind of an extreme example, but the same is true with proofs. Proofs are going to be different from different people. So it's kind of like also with writing programs. Two programs written by two different people are going to have different styles of doing it, and you can even look, if you're looking closely enough, you can see a project that has had several people working on it. You can identify how many different people worked on it because of that many different styles of programming are in the overall project. The result may be the same, but the style and the presentation are going to be different from person to person. Common mistakes. The most common mistakes people make, some of them at least, arguing from examples. We talked about this last time, I think. Just because a idea is true or a statement is true for a few examples doesn't mean that it's true in general. Using examples is only a method of proof if you are proving by exhaustion. If you're dealing with an infinite set, you can't argue from example. Proving a existential statement can be done with an example. Proving that an item exists, but for a universal statement, it's much harder. Like this example they give here, the sum of any two integers is even. This is true because if m equals 14 and n equals 6, which are both even, then m plus n equals 20, which is also even. Therefore, it must be true. Not quite. It's not enough to show just an example that it is true. That might be used as your logic to take on proving the statement. The first step, I believe that we discussed last time, was to intuitively try to determine whether or not the statement you're trying to prove is true. And coming up with a few examples, I was like, well, this might be true. Let's go through a proof and find out if it is actually true. Let's see here. Yeah, you must give an argument to show that the conclusion is true for any arbitrary chosen integers in this case, rather than just giving an example. You can't, it's impossible to go through all even integers and show that the statement is actually true because of the infinity issue. Using the same letter to mean two different things. Using the same letter in when you're for some variable in two different locations, meaning two different things, causes confusion, and it doesn't necessarily work. Like, for example, say m and n are odd integers. Then by definition of odd, m equals 2k plus 1 and n equals 2k plus 1. Well, if that were the case, m would equal n. So you have to choose a different letter for k in one of the two equations. But yeah, think of it as a global variable in a computer program. Once it's introduced, it has the same meaning throughout the program. Its scope extends to the end of the program. That's the scope of this of the defined variables in a proof. The scope extends to the end of the proof. So yeah. So the jumping to a conclusion. This means you allege the truth of something without giving an adequate reason. Consider the following: the proof of the sum of two even integers is even. Suppose m and n are even integers. By definition of even, m equals 2r, n equals 2s for some integers s and r and s. Then m plus n equals 2r plus 2s. So m plus n is even. Well, missing some steps. You're on the right track, but you're missing some steps. You're jumping to the conclusion. You're jumping over steps that need to be shown to demonstrate the validity of the proof. Assuming what is to be proved. This is a variation of the jumping to a conclusion. Suppose m and n are odd integers. When any odd integers are multiplied, their product is odd. Hence, m plus n is odd. You're assuming what you're trying to prove is already proved and just jumping to the conclusion at the end. Doesn't work that way. You got to show the steps. Confusion between what is known and what is still to be shown. A more subtle way to jump to a conclusion, when the conclusion is restated using a variable. Consider this one. Suppose m and n are any odd integers. We must show that m times n is odd. This means that there exists an integer s such that m times n equals 2s plus 1. Also, by definition of odd, there exists an integer a and b such that m equals 2a plus 1 and n equals 2b plus 1. Then you restate the conclusion to be shown. There exists an integer s that you're just restating the conclusion that you're trying to prove without actually proving it. You have to multiply things out and show why this equals this. So see here, we only know that s exists if we know m and n is odd, which is what the author is trying to show. Thus, the sentence starting with the word then, the author jumped to an unjustified conclusion. This could have been avoided if the author had written, "This means we must show that there exists an integer s such that m times n equals 2s plus 1. An even better way to avoid this kind of error is to not introduce a variable into a proof unless it is either part of the hypothesis or deducible from it. Use of any, another mistake, use of any when the correct word is some. Now, sometimes they can be used interchangeably. For example, for any integer n, if 2n equals, or if n equals 2k, where k is an integer, n is even. You could use for any n or for some n. It doesn't matter. But in some cases, you need to show that you need to distinguish between some and any. Any means you could put any number in there. And some means there exists at least one number. Or there might only be one number. So suppose m is a particular but arbitrarily chosen odd integer. By definition of odd, m equals 2a plus 1 for any integer a. That's the wrong word to use because there's only one integer a one integer a that makes m odd, or it would fit this equation. M minus 1 divided by 2. So this here should be some. The correct form of the sentence would be for some integer a. There exists an integer a such that m equals 2a plus 1. Misuse of the word if. Another common error, but is not serious in itself, but it reflects imprecise thinking and sometimes leads to problems later in a proof. Suppose p is a prime number. If p is prime, then p cannot be written as a product of two smaller positive integers. Well, we stated that p is a prime number, so why are we questioning whether or not p is prime? So where the use of the word if is inappropriate there. It suggests the premise of p is in doubt. The primeness of p is in doubt. But p is prime by the first sentence. It cannot be written as a product of two smaller positive integers because it is prime. Here is a correct version of that fragment. Suppose p is prime. Because p is prime, p cannot be written as a product of two smaller positive integers. Because instead of if, to make it clear what's going on. All right. Prove that the difference of any odd integer and any even integer is odd. Use only the definitions of odd and even and the assumptions listed below, not any other properties of odd or even numbers. We went through these assumptions back back on Tuesday. Basic laws of algebra, three properties of equality, substitution, and addition, subtraction, and multiplication are closed on integers. So the following directions follow the directions in this section for writing proofs of universal statements. Well, first state the theorem to be proven. For all integers a and b, if a is odd and b is even, then a minus b is odd. Restate what you're trying to show. Then you follow it with the word proof. Suppose a is any odd integer and b is any given even integer. The conclusion to be shown would be we must show that a minus b is odd. If, in addition, you know how to use the definitions of odd and even, you will have reduced the creative part of developing the proof to a small but crucial section in the middle. So, another example. Find the mistake in the following proof. If n is any integer, even integer, then minus 1 to the n equals 1. Suppose n is the proof is suppose n is any even integer. By definition of even, n equals 2a for some integer a. Then negative 1 to the n is equal to negative 1 to the 2a, which by the law of exponents is negative 1 to the a raised to the second power. Because any non-zero real number is squared is positive, the result is 1. What's the problem with this? Jumps to a conclusion. Although it is true that the square of any non-zero real number is positive, it does not follow that the square of negative 1 to the a is 1. Exercise 10 at the end of the section asks you to give a correct proof of this theorem. Showing that an existential statement is false. Now, we know that the negation of an existential statement is universal. Therefore, if you show a theorem to be true in the universal, then the existential would be false. You show the negation is true, therefore the original statement is false. Show that the following statement is false. There is a positive integer n such that n squared plus 3n plus 2 is prime. Well, given the statement, proving that the given statement is false is equivalent to proving its negation is true. The negation is, for all positive integers n squared plus 3n plus 2 is not prime. So how would you prove that? Negation is universal. It is proved by generalizing from the generic particular. So claim that there is a positive integer n such that n squared plus 3n plus 2 is prime. You have to prove that this is false. The proof would be, suppose n is any positive integer. Factoring that shows 2 squared plus 3n plus 2 equals n plus 2 times quantity n plus 1. In addition, n plus 1 and n plus 2 are integers because they are sum of integers. And both n plus 1 is greater than 1 and n plus 2 is greater than 1. N, because n is greater than or equal to 1. Thus, the equation is a product of two integers, each greater than 1. Therefore, by the definition of a prime, n squared plus 3n plus 2 is not prime. And that would just about wrap it up for this section. I don't believe we have time for another section. Well, I guess we do. It was a short one. So, elementary number theory and methods of proof. Getting into the second one, or the third one, rational numbers. Direct proof and counterexamples, section 3. Definition. A real number is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. A rational number is not rational, that is not rational is irrational. More formally, if R is a real number, then R is rational if and if only if there exists integers a and b such that R equals a over b and b does not equal to 0. So, is 10 over 3 rational? Yeah. Is 5 over 39 rational? Two integers, so yeah. Is 0.281 a rational number? Yeah, because it's 281 over 100. Or over 1,000, yeah, sorry. Basic math, it gets me every time. Is 7 a rational number? Yeah, 7 over 1. 0 a rational number? I'm sorry? Yeah, it's 0 over 1 would be an integer, would be integers. 2 over 0 rational? No, because the denominator can't be equal to 0. 2 over 0 irrational number? Because it's not rational, yeah. So, is 0.121212 and so on a rational number? I believe it is. Where m and n are integers and neither m nor n is 0, is m plus n over m times n a rational number? Yes, because the sum and product of integers are also integers. And the denominator wouldn't be 0. So, yes, yes, yes. No, 2 is not. No, because of reverse. Okay. No, because 2 over 0 is not an irrational number because it has to be a real number, and 2 over 0 is not a real number. Forgot about that. It's infinity. It's not an actual number. As the denominator approaches 0, the value approaches infinity.
Oh yeah, because you get divide.
Yeah. Yeah. Let's see here. Yes. Okay, so yeah, 1, 2, 1, 2, 1, 2 is 12/99. So it is a ratio of 2 non-zero integers, and thus is a net rational number. Hence, yes, m and n are integers, so m plus n and m and n are integers, because summing products of integers are integers, and m and n, m times n is not equal to 0 by the zero product property. That property is, if neither of two real numbers is 0, then their product is also not 0. More generalizing from the generic particular. Most problems are stated in informal language, but solving them often requires translating them into more formal terms. Like, every integer is a rational number. So, proving properties of rational numbers. Prove that the sum of any two rational numbers is also rational. Well, begin by mentally or explicitly writing the statement to be proved in the form of, for all blank, if blank, then blank. For all real numbers R and S, if R and S are rational, then R plus S is rational. Next, ask yourself, what am I starting from? What am I supposing? That gives you your starting point. First sentence of the proof. Suppose that R and S are particular but arbitrarily chosen real numbers such that R and S are rational, or more simply, suppose R and S are rational numbers. What must I show to complete the proof? R plus S is rational. Finally ask, how do I get from the starting point to the conclusion? Or, why must R plus S be rational if both R and S are rational? The answer depends in an essential way on the definition of rational. Rational numbers are quotients of integers, so say that R and S are rational means that R equals A over B and S equals C over D, such that A, B, C, and D are integers, and B and D do not equal 0. It follows by substitution that equation is true. Now you can show that the right-hand side of the equation equals the left hand by rewriting the fraction with a common denominator, and then adding the fractions with a common denominator. And then, since A, B, C, and D are all integers, the ratio is with an integer over an integer. Why is that going? It's not the first of the month and it's not noon, so. So there is R plus S is a rational number. Deriving new mathematics from old. Suppose that you already proved the following properties of even and odd integers. The product and sum and difference of any two even integers is even. Sum and difference of any odd integers are even. The product of two odd integers is odd. The product of any even integer and any odd integer is even. Did I say that right? The product of any even integer and any odd integer is even. Yeah. The sum of any odd integer and any even integer is odd. The difference of any odd integer minus any even integer is odd. And the difference of any even integer minus any odd integer is odd. Use these properties listed above to prove that if A is any given integer and B is any given odd integer, then this is an integer. Well, then you wouldn't need all 7 of those properties. But yeah, we're gonna go through it and suppose A is an even integer and B is an odd integer. By property 3, B squared is odd, and by property 1, A squared is even. Then by property 5, A squared plus B squared is odd. Because 1 is also odd, the sum is even. Hence, by definition of even, there exists an integer k such that A squared plus B squared plus 1 equals 2k. Dividing both sides by 2 gives A squared plus B squared plus 1 over 2 equals k, which is an integer. Thus, the equation is an integer. Derive the following as a corollary of the previous theorem. The double of a rational number is rational. Double of a number is just its sum with itself. But since the sum of any two rational numbers is rational, the sum of a rational number with itself is rational. Hence, the double of a rational number is rational. And the proof is just a couple, 3 sentences? Yeah. And this was a brief section. Oh, okay. But yeah, derive theorems, use them for further proofs, and avoid the pitfalls and mistakes that were stated in the previous section. I guess that would be about it for today. Have a wonderful day. Brief as it was. I will see you on Tuesday.